Um, Today's experiment is experiment number 4, and it's all about the separation of compounds using physical methods, and we'll be using some physical methods to separate or some compounds from their own actual mixture. So before we are starting this discussing separation methods, we'll be working on, as I will mention, on the extraction methods. So methods of separations, there are several methods available to us. And as you can see, the first one is can be filtration, distillation, evaporation, which is boiling, crystallization, chromatography. So the first one is filtration. The second one, decanting. The third one, distillation. The fourth one, extraction. The fifth one, of course, you know that's chromatography. So we took an experiment, TLC, chromatography, which is a solid chromatography, solid liquid chromatography. And the chromatography has different types. Can be gas chromatography, can be liquid chromatography, and can be just gas, liquid, or paper chromatography, which is solid chromatography. And there is one last one we can mention. If you look at all those filtration, decanting, distillation, extraction, and chromatography, we can add crystallization. Crystallization is another method to use to separate compounds from their own mixture. And all those methods are very, very important in separation of compound from their own original mixture. So the sixth method now I'm writing here for you is called crystallization method. Of course, today we'll be concentrating ourselves in the fourth type of separation. We'll be concentrating ourselves on the extraction method. And as you can see, in this method, extraction method, it has several types, but we will be concentrating on ourselves solid liquid extraction and liquid extraction. Let me write it down. The first one is solid liquid extraction. The second one is liquid extraction. And both methods here are very, very important in separating compounds from their original mixtures. In the solid, the first procedure, solid liquid extraction, will be extracting lipids out of snack food. Okay, we'll extract lipids out of snack food. And in the second procedure, liquid extraction, will be extracting caffeine out of soda or cola. So those are the two type of experiments we will do today. Going back and looking at those two procedures in some details, we will be looking at those procedures in some details. The first one is solid liquid extraction. As we said, that we are extracting lipids out of snack food. Now you might ask, what are those lipids? Well, it turns out to be lipids are organic compounds that are not really soluble in H2O, in polar solvent, but they are soluble in non-polar solvent. So organic compounds, they have unique physical property that they are not soluble in polar solvents such as H2O. However, they are soluble in non-polar solvents such as hexane today. Like we'll be using hexane as a solvent. Hexane is non-polar solvent or compound. I'm just writing whatever I told you. They are soluble in non-polar solvents such as hexane. We'll be using hexane today to extract the lipids out of the food snacks. I'm just writing you whatever I told you. Hexane. Hexane is C6H14. Is an alkane. C6H14. 6 carbons and 12 hydrogens. Okay. After we knew the meaning of lipids, we have to go in some details about the procedure steps, which is really not really difficult. As you can see, we'll be crushing this snack food in a mortar and pestle, and then trying to take this food out of the mortar and pestle by using hexane. We are purging the whole lipids, crushed lipids, with the help of hexane. Now the hexane will dissolve the lipids inside the snack food, but will not dissolve any polar compound in that snack food. So just whatever I told you now, I'm just drawing the whole mortar and pestle, and there you have, we will weigh a specific amount of our snack food. We'll crush it first. Crush the snack food with the pistol, and then crushing it will facilitate the nonpolar solvent hexane to extract the lipids out of these crushed snack food. I'm just drawing for you the steps here. As you can see, it's very important to be really consistent with the crushing. You have to really crush this one here to make easy situation for hexane to come and extract. If those are the snack foods are very large, the hexane will have a hard time to dissolve or extract these lipids out of this snack food. So, in the meantime, while we are crushing here, we can brew or small tiny beaker, 150 ml beaker. We have to know the weight of it. It is very important. And we have to put 3 to 5 boiling chips inside it. So we have to weigh the beaker, 150 ml beaker, with the boiling chips, both. Nothing inside them. We call this one here beaker plus boiling chips empty. Empty. Okay? And then we keep this one here empty. We take, we decant the hexane with the crushed snack food. We'll avoid any transfer of this crushed particles of the snack into the beaker. So we'll take the hexane with the lipid extract into that beaker and take the whole thing in the hot plate. The stirrer of the hot plate should be off. However, the heater should be on and should be in the middle. Why is the middle? Because we have to heat the hexane to get rid of the hexane, but the heat has to be mild. Not too cold, not too hot. Mild, in the middle. So, we'll take the beaker now filled with the hexane and the lipids, okay, into the beaker. Now make sure that after crush the snack food, you add more extra hexane and crushing. Do this one 2-3 times to make sure that all the lipids is out of this crushed food. Okay, guys? And you will take then the pipette, okay? Use pipette inside this mortar and pistol to take the top layer, the hexane layer out, and then pipette it into the beaker. That's before heating, of course. And now you are ready to heat for a couple minutes. And the snack food, as I said, the small tiny amount is 5 to 6 grams, at the beginning. So you have to weigh the snack food exactly. It has to be between 5 and 6, but you have to exactly know the mass of this snack food. So now we'll start boiling after making sure that every lipid molecules are taken away by hexane. Okay, we will repeat the pistol mortar crushing couple times inside, so to make sure that everything is crushed and everything is taken by hexane. And you can add extra hexane, just to make sure that everything is extracted by hexane. Okay, guys, and make sure that you take the pipettes to help you not to add any particles of the crushed snack food, because that will change your yield when you start calculating the actual yield. So, after decanting the whole hexane with the lipids into the beaker with 3 to 5 boiling chips, we start boiling mild Mild heat, the indicator of the hot plate is in the middle. For a couple minutes, I would say maybe 5 minutes, 5-10 minutes. Hexane will evaporate at these temperatures. So it will evaporate, then leaving our boiling chips with our lipids inside the beaker. Now, after heating, the mild heating for, say, 5 to 10 minutes, to make sure that all the solvent hexane is evaporated, I will go and take the beaker, put it aside. Of course, all this evaporation using the hot plate, it has to be in the hood. It has to be in the hood, nothing on your bench. You don't want to inhale toxic vapors or something. Everything in the hood. You will cool down your beaker, and then cooling down the beaker, you go and wait. Now, the mass of your caffeine will be mass of the caffeine plus beaker plus boiling chips filled minus the beaker with boiling chips empty. So the beaker is filled with the caffeine and boiling chips minus the beaker with the boiling chips empty will give you the amount of caffeine. Not caffeine, sorry. Amount of your lipids. I'm sorry, I apologize. I said caffeine. That will come in the next step, liquid extraction. I apologize. Now, with this information in mind, this will be your actual yield. Then you go to the snack. In the back of the snack bag, you have to know how to read those total fats written or given regarding in the whole servings, and then calculate your fat or lipids inside your sample. Your sample is whatever your sample is, 5 to 6 grams. So with this, the whole calculation is, I'll show you the whole calculation in a couple of minutes. So then you will have your theoretical yield from the bag back, all the information there, the mass of total fat divided by the whole total serving grams, equal to the X amount of lipids or fats divided by the amount of your sample. So that will give you your theoretical. Your actual, that's what you got. Your beaker is filled with your beaker filled with the lipids, correct? And boiling chips minus the beaker with boiling chips empty, no lipids inside. That will give you the amount of lipids there. And this is all the information here. Make sure you don't overheat, because otherwise what will happen when you overheat, if you overheat, although you are using boiling chips, that might not help, and you'll be the whole hexane solvent will be vigorously evaporating, taking all the stuff with it, and you lose some of your lipids. And that's one. The second one, might harm your eyes or your body parts because of the hot liquids hot solvent hexane coming in contact with your body. Here we talked about how to calculate the theoretical, correct? The theoretical yield. You compare your total fat, correct, 12 grams, to the whole serving total, which is, here in this example, you have 12 grams of total fat to the whole servings. That you can find it inside, in the back of your snack, equal to X gram of lipids or fats. That's what you are looking for. You don't know. Divided by the amount you have taken from 5 to 6 grams. So in this case, 5.5 grams. You calculate this and you calculate X. X will be your theoretical field. Now, after this, after your procedure, you calculate the actual amount of lipids. As I said, beaker with boiling chips with the lipids filled minus beaker with the boiling chips empty. That will give you the actual yield. Actual yield over theoretical yield from the back of the snack bag multiplied by 100 will give you what? Will give you the percentage, overall percentage yield. The overall percentage yield. So that's the 1.65 grams. That's your theoretical yield. And you assume that in the example here, your experimental yield or the actual yield, call it the experimental yield, the actual yield is 1.23, just an example, divided by the theoretical yield from the information from the back of the bag of the food snacks, multiplied by 100. That will give you the overall recovered lipids percentage. Okay, percentage of the total lipids recovered. Now we'll be looking into the fact of this second procedure, which is liquid extraction. But before going that one, I might ask, any question do you have? Any question? Any question you have, please? Any question before we go further? Now I want to show you this type of, when I say the type of lipids, how they look like here. Lipids are compound coming from glycerol, that's trialcohol, and tri-fatty acids. Those are carboxylic acids, but fatty acids. Fatty acids, they have too many carbons, up to 20 carbon atoms. So, and the fatty acid, they have two parts, one nonpolar, which is the long chain, alkane chain, and the carboxylic group, which is a polar part. So if you look at this, so what will happen is the OH from the fatty acids will be taken by the H of the alcohol, of the trialcohol, which is glycerol. I apologize, might be. Now, if we add them up, okay, H2O will be taken out. The glycerol will contribute with the H proton, and the carboxylic acid will contribute to the OH. You get H2O. Since you have 3 fatty acids, you can produce 3 molecules of H2O. Okay? And this called here, that's an ester, by the way. This is called an ester, which is really made of glycerol with 3 alcohol hydroxyl group and fatty acid with 3 carboxylic groups. So that's a fatty acid, that's an ester. Ester always a combination of alcohol with carboxylic acid. This carboxylic acid is a long chain of carbon, up to 20 carbons. So that's called fat. That's called fat or oil, depending on, we'll see what's the difference between them in a minute. That's an ester, combination of alcohol plus carboxylic acid. Since you have 3 alcohol, you need the 3 carboxylic acid. So you produce 3 H2O. And the glycerol called what? Triacyl glyceride. So the whole ester is triacyl glyceride. Now we have an ester, which is lipid. Now this lipid, depending on the single bond or double bond. If you have the 3 carboxylic acid, no double bond, this is fat. But now if you add introducing double bonds to this carbon chain, then you speak about what? You speak about oil. Now this is oil. Now when you add carboxylic acid with double bond, this is oil. This is called oil. And oils are liquid at room temperature. Fats are solids at room temperature. And fats, they have carboxylic acid. The chain of the carbon chain is single bonded. The oil, the carbon chain has suffered double bonds. And oils are liquids at room temperature, and fats are solids at room temperature. And the whole thing called fats and oils in general, the whole thing is called lipids, because both of those fats and oils are not soluble in H2O. And that's the reason lipids are compounds. They are not soluble in polar solvent. They are soluble in non-polar solvent, such as hexane in our example. So everybody's following? Everybody's following? Please let me know if you have any question. So the difference between fats and oils is the single bond versus double bond. If I have the carbon chain only with single bond, the three carboxylic acid with single bonds, that's fat, which is solid at room temperature. The oils, you have carboxylic acid, 1 or 2 of the 3, or 3 of all of them 3, they have double bonds. So that's oil, and those oils are liquids at room temperature. Now, sometimes we have to know how the reaction of those lipids. So we are combining the alcohol with the carboxylic acid to get ester. You can get back again, if you hydrolyze fats and oils, you get back alcohol and your carboxylic acids. So the reaction is really reversible. Now let's look at the second one, which is liquid liquid extraction. I'm just looking at the whole thing, and it's time to look into the liquid extraction. But before going anywhere, so I'm just asking if anyone has any question, please. Any question, please. Let me know. Any question about the first part? I'm not going in details. All the procedures there, I give you the whole overall ideas and concept of the content of the extraction method of solid liquid extraction. Okay, guys, time to go to the second procedure, which is liquid extraction. What we are doing in this procedure here, we are taking caffeine out of soda, out of cola. We have to use a solvent that's not, caffeine is highly soluble in it and less soluble in the cola. The cola or soda has H2O, so the caffeine is soluble in H2O inside cola. However, the solubility of caffeine is very high in solvent called ethyl acetate. So ethyl acetate is organic, so caffeine is an organic compound. So organic compounds will like to be dissolved in organic solvents. Okay, caffeine is polar, as you saw its structure. It has nitrogen with the free lone pairs. So at the bottom you will see our soda, which has content of H2O and caffeine, and the ethyl acetate in the top. You will be wondering, why is the solvent ethyl acetate in the top while caffeine darker color, which is dissolved in H2O, at the bottom? Well, it turns out, as you see, I will mention it in a couple of minutes. Let me finish here writing. So ethyl acetate in the top. Why? Well, it turns out the density is very important. Caffeine dissolved in H2O, so the density of H2O is 1 gram per ml, and the ethyl acetate is 0.99. I'll write you the information in a couple of minutes. But meantime, so ethyl acetate is less than 1 gram per ml, it's 0.99. So ethyl acetate will float over H2O. So now you tell me how you get the ethyl acetate. We can go over it quick. Ethyl acetate is an ester, as mentioned with this fat and lipids. Those are esters, organic esters, of course. This ethyl acetate is organic ester, but this is polar now. Those are polar. The fat and oils esters, but non-polar. So what will happen is the carboxylic acid, which is acetic acid or ethanoic acid, will donate its OH group, and the alcohol, ethanol, will donate its proton. So then you have H2O will come out of this, and then you will have ethyl acetate. Ethyl acetate, that's a common name. I will mention it in a minute. This is ethyl acetate. Is just you combine the carboxylic acid, ethanoic acid or acetic acid, with ethanol, and the H2O will come by as a byproduct. And this is called ethyl ethanoate or ethyl acetate. The ethyl ethanoate is IUPAC name, and the common name is ethyl acetate. So IUPAC name is for ethyl ethanoate, and that's the exact name. And the common name is ethyl acetate. So that's a solvent. The caffeine is highly soluble in it than H2O. So we can use this fact to separate both, separate caffeine, extract caffeine out of H2O. So the caffeine will, most of the caffeine will go in ethyl acetate phase or layer, and the H2O will come at the bottom. And the H2O will stay at the bottom. The caffeine, most of the caffeine will go up in the ethyl acetate layer. And then the H2O will have still small amount of caffeine, and then we'll discuss how to get most of the caffeine out of the aqueous phase, out of H2O layer. So that's here what I promised you to, that's the density of ethyl acetate is 0.9 gram per ml. H2O is 1 gram per ml. So H2O is dense, heavier, so it will sink at the bottom layer, and the top layer is ethyl acetate. So the extraction or the separation is really based on the not polarity, because both H2O and ethyl acetate solvent are polar, but it's really, we separate them due to their differences in densities. And of course the solubility, to some extent, solubility of caffeine in ethyl acetate is higher than the solubility of caffeine in H2O. Of course, what I have drawn to you called extraction funnel. Extraction funnel. Sometimes called extracting funnel, but extraction funnel or extracting funnel is a funnel used to separate two liquids from each other depending on their densities and solubilities. I mean, separate a material or a compound out of two different solvents due to differences in their densities and solubilities. So you have to secure this extraction funnel. So what will happen here, let me just explain to you what will happen. You take this funnel, you do the whole thing inside the hood. Okay, you put the lid on the extraction funnel, you shake it a couple of times, and then carefully straighten up the shaking with the, at angle, not straight, but at the angle. And then you straighten the whole thing and put the extraction funnel inside the O-ring and vent, take the lid slowly out, let it vent and let it settle down a little bit without the lid. So you will see with shaking, you will see most of the caffeine is really diffused into the ethyl acetate layer, the top layer. Okay? So what you will do next, you will do this one for a couple of times, correct? You will do this one for a couple of times. Then you will start extracting the top, not the top, but the bottom layer, which has H2O and a little bit of caffeine still there, might be there, correct? There is a possibility, strong possibility possibility that you have caffeine still in the bottom layer of H2O. Take the whole bottom layer out in a small beaker. Keep it aside. Correct, guys? And then what you will do here, you will add to this extraction funnel a little bit of 5 mL, whatever. You have not to count how many milliliters, but you add ethyl acetate to it. Again, you will have to add ethyl acetate to it. Why? Because whatever is H2O is still there the ethyl acetate will, caffeine inside the ethyl acetate there will be extracted into ethyl acetate, and then see if you have two phases. You get rid of the bottom one, add the bottom one layer into the beaker with the H2O layer. You drained it at the beginning. Okay, guys. Now, with this in mind, you'll add to the beaker of H2O. Okay, the bottom layer, you add ethyl acetate to it. How about that? Why? Then you have to take the beaker, the top, the decant, the top layer, which is ethyl acetate plus extracted caffeine from the aqueous solution, from the bottom layer, and put it inside, and you shake it a couple of times, and you try to get rid of the two layers, the bottom layer, get rid of it. And then I think most of the time you have taken most of the caffeine out. You can try this one twice or 3 times. And now you are ready to add the whole liquid from the extracting funnel into a pre-weighed beaker with boiling chips. Again, the same thing we did the first step. You boil it to get rid of first, before boiling it, you put sodium sulfate solid to take away the H2O. Whatever H2O inside the top layer will be taken by the solid crystals of sodium sulfate. It's a drying agent. So then when you decant the whole thing, ethyl acetate, you keep this one for a couple of minutes, say 10 minutes. The sodium sulfate is inside to take out any leftover H2O inside that layer, the top layer. So then you decant the whole thing into a pre-weighed beaker with 3 to 5 boiling chips. You dry the ethyl acetate, you cool down the whole thing, and you weigh the whole beaker, and then the difference will give you the amount of caffeine. What's the difference? The difference of the beaker with the boiling chips, the new one, the last one you have taken, filled with the caffeine minus the boiling chips with the beaker empty. That will give you the mass of your caffeine. This one we will not say how much you recovered, but at least direct grams will give us. So we can determine if we know the density of the solution of soda, we can calculate, but we will not do that. But at least we record how many grams you get of this caffeine. Now, as you see, those unique compounds, they have those compounds are highly stimulant, and all of them, this caffeine and those caffeine type of compounds, those are called stimulant and addictive. All of them, they have nitrogen, as you have seen. They do have nitrogen in them, which keep them really very, very addictive and very aggressive on the brain cells. So I think with this, you know how to do it. I'm not going into the details. You can read the details of the procedure, but I gave you the whole concept of the whole 2 procedures: solid liquid extraction, liquid extraction. The solid liquid, we extracted lipids, which can be fat or oils from the snack food. And then the liquid, we extracted caffeine out of soda. And we, in both cases, the first case we did the percentage yield, which is actual divided by theoretical multiplied by 100. The second one, we did not do the percentage yield, but we just calculate how much grams of caffeine we have recovered. So I think that's the whole thing about the experiment. As I said, Please go through all the steps of the procedure, step by step. And if you have any question, come and see me. I'm here in the lab for you, and I will cover any questions you have. As I said, make sure that whenever it's heating, do not overheat. In both procedures, avoid overheat. Overheat will destroy your yield and will cause harm to your body. If something will spill over to your body and jump to your body, so that's not good. That's hot liquids of the solvent, which is one is hexane in a solid liquid extraction, and one is ethyl acetate in the liquid extraction. So any type of question, please come and see me. Just record all your data inside those tables given to you, and please come and see me. Come and see me. If you have any extra question, I'm here, available to you anytime. And don't hesitate to ask any questions you have. Okay, guys, I'm just repeating myself, so if you have any question, please don't hesitate to ask. I'm here for you. And this is straightforward. Experiment is not really difficult. Calculation is straightforward. And you have a question, let me